very much, Ludmil, for the introduction. Thank you, of course, for the invitation. So I'm really honored to speak at the conference for Maxim's birthday. And maybe am I supposed to say some anecdote? I don't really have any anecdote for Maxim, because I think with Maxim we always talk about the mathematics, and that's something I really enjoy. Maybe the only non-mathematical thing I did with Maxim is once we went to pick mushrooms together with Matthias and
what kind of mushroom?
I don't think the mushrooms in Paris have any special power. Just at least it didn't help to solve mirror symmetry after the mushrooms. So okay, it's joint work with Ludmil, Maxim, Pantev, and also my student Hinault, Zhang, and S. So let me continue with my talk. Yeah, so I'll give the motivations from non-commutative Hodge structures, and then I will review the analytic decomposition theorem of non-commutative Hodge structures from the work by Ludmil, Maxim, and Pantev. And then I guess you already see the definition, the theory of F bundles in last year's conference. Let me talk about it, review it again. And then I'll talk about the two theorems regarding these F bundles. One is the spectral decomposition theorem, and another is the framing for theorem for F bundles, and both are fundamental properties of F bundles that are used in the application to birational geometry. And finally, I'll discuss application to the decomposition of quantum cohomology. And of course, all the theory is set up for the application to birational geometry. And we are working on more refined notions of F bundles in order to explore more stronger birational invariants. So if you have any questions, please don't me during the talk. Yeah, so the motivation for F bundles really come from these non-commutative Hodge structures proposed in the paper by Katzarkov, Kontsevich, Pantev. I don't know if you know the definition, but it's kind of long. So rational pure non-commutative Hodge structure consists of three things. Z2 graded algebraic vector bundle on A1, and we put coordinate U for A1. H, so H is a vector bundle on A1. And then we also have some local system of finite dimensional Q vector spaces on A1 minus 0. Then there is some compatibility between the local system and the vector bundle. So we say that the local system generates the vector bundle in the sense that we have a isomorphism between local system tensor with the sheaf of functions with the vector bundle outside. So now since we
sorry, can you remind me, analytic, is it neuromorphic at 0 or analytic? Analytic isomorphism?
Analytic isomorphism is
okay,
not about 0. It's just outside the 0. Okay. Thank you for the question. Yeah. So now since we have since the local system generates the vector bundle, we see that we get a flat holomorphic connection on the vector bundle outside the 0. So it's actually very simple, just the vector bundle together with the Q local system. Okay. But we have a few requirements, few axioms on this data. First, there is this NC filtration axiom. We ask this induced connection nabula to be a meromorphic connection on the vector bundle with a pole of order 2 at u equals 0 and a regular singularity at infinity. So it's just the two poles, 0 and infinity. At 0, it's pole of order 2, and at infinity, it's regular singularity. And the next, we also ask some, it's called the Q structure axiom. We also ask for some compatibility between the Q structure and the connection. So we say that this local system, Q local system, is compatible with Stokes space. Roughly, it means that if we consider this, since it has a pole of order 2, you can't really find the solutions around the 0. All you can do is to find solutions on sectors around the 0, and then you look at the asymptotics of solutions, you get the Stokes filtration, and we ask the filtration to be compatible with this local system, meaning that if you intersect the filtration with the local system, you can still generate the filtration. Okay, and finally, there is this opposeness axiom, which is a generalization of the classical Hodge theory. We ask in classical Hodge theory, we ask that the complex conjugation of HPQ is HQP, and there is a way to reformulate it into this non-commutative Hodge structure. So that's this really nice notion in the KKP paper. But it seems a bit, still a bit complicated, especially that these axioms are hard to check, even for very basic examples. So if it's your first time seeing the non-commutative Hodge structure, we have an example showing how a rational pure Hodge structure of a given weight W can be seen as a non-commutative Hodge structure. So for usual Hodge structure, we have a Hodge filtration. In the non-commutative Hodge structure, we don't have Hodge filtration. We have the extra variable u, and we just use the extra variable u to encode the Hodge filtration. There is this reconstruction. We put powers of u there to remember the Hodge filtration, and then we also have the connection nabula, and the local system is given by the Q structure of the Hodge filtration. Okay. And a lot of, I guess it's expected that all the examples of non-commutative Hodge structure from mirror symmetry should be of exponential type, which is a special, it's a stronger condition on the singularity at 0. We ask the singularity to have second order pole at 0, and but moreover, if it's of exponential type with exponents b1 to bn, complex numbers, if this non-commutative Hodge structure splits like this. So we know by the Lebel-Turretin theorem, when we restrict to this formal punctured neighborhood, it's split, but not necessarily in this form. And sometimes we also need a ramified cover. So here it's said to be of exponential type if after this tensoring it is split into this simple form. So it's some rank 1 bundle tensor with some connection with regular singularity. And on this rank 1 bundle, we have the connection given by b minus b di over u. Now, for priori, you might get more complicated things. It's said to be of exponential type if it's of this simple form. So of course, here I introduced the notion of non-commutative Hodge structure. Since we can also consider families of non-commutative Hodge structures, and it's called the variation of non-commutative Hodge structure over some base. Okay, so here of course, now you can consider examples of non-commutative Hodge structures from A model, from B model, and you have this A model non-commutative Hodge structure given by Gromov-Witten invariants, and the B model non-commutative Hodge structure given by this. You consider this twisted theorem, cohomology, and the Gauss-Meinong connection. In the A model case, so then of course you want to ask whether all these properties are satisfied. In the A model case, I guess the NC filtration axiom that's directly from the definition, and the Q structure axiom, it's very hard. It's related to the gamma conjecture. There are a lot of works by Iritani and many other people on gamma conjecture. And opposed to this, I guess nobody worked on the opposedness. For the exponential type, there are recent works by Paul Seidel and his student Zhang and S showing for monotone reflective because we have exponential type. And in the B model, I guess we know more. In the B model case, the literature may be a bit like complicated. In the B model case, there are works by Sabat showing and other people showing the properties. Okay. So anyway, it feels a bit that there are a lot of structures and not easy, and many properties are conjectural, so not so easy to use. And that's why later we have this F bundle, which is a simplified formal version of this non-commutative Hodge structures. Yeah, so next let me talk about analytic decomposition of non-commutative Hodge structures. Of course, why do we want to decompose it? Because eventually we want to apply to this birational invariance, where we decompose a variety into elementary pieces. And here, let's see, given a non-commutative Hodge structure, actually we can get some decomposition from its Fourier transform. Here is maybe let me first show this part. Okay. So you remember in the non-commutative Hodge structure, we have this connection. We have vector bundle local system. This induces a connection. So we have this connection part, and the connection part, we call it the round data, which is algebraic vector bundle. It is a vector bundle. The vector bundle H with connection nabla on A1 minus 0. In the definition, the H is over the whole A1. It's like a static or a connection, but it's okay. Let's just have H with connection nabla on A1 minus 0, and the singularity of exponential type at 0, regular singularity at infinity. If we apply Fourier transform to this connection seen as a D module, we can get a regular holonomic D module M on A1 with regular singularities everywhere. So after Fourier transform, before we had just two singularities, one at 0 and another at infinity. After Fourier transform, we will have many singularities on A1, but they will all be regular. That's the equivalent to this singularity at 0 being of exponential type. So exponential type there translates to regular singularities after Fourier transform. And furthermore, we have vanishing the round cohomology. So if I take the round cohomology of this regular holonomic D module M, we get 0. And now let's see how the Betti data or the Q, the rational data transforms under this. So this rational structure, the Betti data and the round data, they are related by the Riemann-Hilbert correspondence. On this side, it's the singularity of second order pole, so we have irregular Riemann-Hilbert correspondence. And on the right-hand side, after Fourier transform, it's just the regular singularity. So we have the regular Riemann-Hilbert correspondence. And when we consider the irregular Riemann-Hilbert, we get the Stokes structure. We get some Stokes structure of exponential type, and the rational structure is just the Q-Stokes structure. Then on this corner, where we apply a Riemann-Hilbert, there we get a constructible sheaf. Of course, first we get some perverse sheaf, but one can show that it's in this case it's equivalent to a constructible sheaf of rational vector spaces in vanishing cohomology. And these Q structures are related by so-called topological Laplace transform. Okay, so this is just a general picture of Fourier transform and the Riemann-Hilbert correspondence. We hope that we can also extend it to non-Archimedean geometry, because later you will see that we will move from complex analytic geometry to non-Archimedean geometry, both for our application to birational geometry and also for getting rid of all these hard conjectures about convergence for this Gromov-Witten invariant. Okay. So, but in non-Archimedean geometry, the picture is much less clear. We don't know what to do yet for the local system, constructing the sheaves, and Riemann-Hilbert. Okay. But once we have this picture, it suggests us some decomposition of, we want to do some decomposition of this non-commutative Hodge structure. And when we have this picture, we can decompose non-commutative Hodge structure by choosing some path, like this called the Gabriel path. So the C1 to Cn, they are exponents of the singularity of the connection at 0. So you remember now it's the connection at 0 is supposed to have this exponential type. So we have these exponents C1 to Cn. They are just the complex numbers, and they are the same. These complex numbers are the same as exponents of this Stokes structure, or under the topological Fourier transform, they are the same as singularities. Under the Fourier transform, they are the same as the singularities of this D module, and under the topological Laplace transform, they are the same as singularities of this constructible sheaf F. Okay, so now we just draw this point. This we can think of either as singularities, exponents, or singularities, and then we choose some point far away, C0, and draw this path from C0 to somewhere near this singular point. If you are thinking that's how you do Fukaya-Saito category. Okay. And once we have this Gabriel path, it gives us a decomposition of this constructible sheaf F into combinatorial data. And this is called the vanishing cycle decomposition. So once we choose this path, we get a decomposition of this constructible sheaf F. Here, the constructible sheaf, it not that complicated. It's like around every point, you have constructible sheaf on the disk, and then it's a local system outside of the singularity. So all you have to do is just decompose it into a collection of U1 to UN or finite dimensional Q vector spaces, which remembers what happened at every singularity, and then collection of linear maps. It's gluing data. How to reconstruct this the whole sheet from these finitely many vector spaces.
Sorry, I'm getting lost here. Can you explain more precisely, I mean, concretely, what the Tij do when I have an actual, how do they relate to the actual F?
You look at the monodromy, and then basically you look at all the monodromy matrices, and the Tij will be components in the matrix.
Oh, so the UIs are meant to be a direct sum?
Direct sum, yeah, it's looking at the direct sum of UIs, yeah.
Ah, okay. Okay. See, thank you.
Thank you, Denis, for the question. Any other questions?
What is F Laplace transform?
F is the topological Laplace transform of this Stokes.
And why is it constructed?
Oh, because if you apply Riemann-Hilbert here, it's Riemann-Hilbert. You apply Riemann-Hilbert. Why is it constructible? It's very simple. It's just a local system outside of these singularities, and it's just by definition. And but of course, when you apply Riemann-Hilbert, or you get a D module. Yeah, but sorry, you apply Riemann-Hilbert to the D module, you get a perverse sheaf, and then one can show that the perverse sheaf is concentrated in degree -1. Oh, if I'm correct. And if you take what's on that degree, it's a constructible sheaf. But I really like this story. It's in the KKP paper. This is not. It's kind of elementary, but not trivial. Okay. Yeah, and from this decomposition of constructible sheaf, we can get an analytic decomposition theorem. So we can decompose not just this is decomposition of constructible sheaf is like decomposition of the Betti data, but now you combine decomposition of Betti data with decomposition of the RAM data, and also there is this lattice information, this vector bundle over A1. So you combine everything, and we can get this analytical decomposition theorem from this KKP page. So it says that a non-commutative Hodge structure, this H, vector bundle H, local system E, as one system ISO can be decomposed into the following data. First, we remember these finitely many points, C1 to Cn in the complex plane. And then we decompose this non-commutative Hodge structures into a collection of non-commutative Hodge structures with regular singularities. Now there are no more irregular singularities 0. Now it's just a collection of them with regular singularities. And then we have gluing data. Gluing data is when he was asking, that's Tij.
Sorry, the Tij is part of the monodromy for which loop?
No,
It's not for a loop. It's
a bit more complicated. Yeah, one can write using Tij and monodromy around everything in some certain way. Yes. Okay.
Like you take monodromy and then you get a bigger matrix, and the Tij is one entry in the matrix.
Maybe we should go around. I suppose that will be identity matrix plus a column, and column fits will be Ti flips and J.
Yeah, but what's really nice is that you can just use this linear algebra, some vector spaces and some linear transformations to describe the whole thing. Okay, so that's also part of the motivation, because now I want to use this motivation to talk about decomposition of doing it in a formal or non-Archimedean way. This is the idea in KKP paper, doing this decomposition in the analytic way using Fourier transform. Okay, so let me just recall what are F bundles. The reason we have to introduce F bundles is because many conjectures regarding non-commutative Hodge structures are too hard. We have no idea how to solve them. Probably Maxime had and Ludmila and Tony had ideas about applications of non-commutative Hodge structures for a very long time, but since we can't even prove that the A model non-commutative Hodge structure is a non-commutative Hodge structure, so we can't really use. So that's why we have to introduce this simpler or formal notion called the F bundle. The idea is just we ignore complex convergence and also we ignore rational structures, and there we get F bundle. Hopefully we can put rational structures back into the story. But we still ignore complex analytic convergence, but hopefully we can get some rational structure in the non-Archimedean setting as well. And these are needed for applications for stronger birational invariants too. Okay. Okay, so we use non-Archimedean geometry to avoid complex analytic convergence. Therefore, now we choose some base B to be some smooth non-Archimedean K-analytic space. And also just now we had some vector bundle over A1. Now we also get rid of A1. Because probably over, so I want to say we get rid of A1 and we just consider germ of 0. B. For this extra variable U, we just consider a germ of 0. In the complex case, probably they are equivalent. I'm not sure about the non-Archimedean. Okay. Okay. So F bundle is a formal simplified notion of a variation of non-commutative Hodge structure. It consists of a vector bundle. So F bundle H nabla over B. It consists of a vector bundle H over now B times the germ of 0 D. Before it was B times A1. And we also have a meromorphic flat connection nabla. Since we now no longer consider this Q structure, anyway, even if we want to consider Q structure, we can't do it as in the complex case because we don't have this local system. Don't really have a good local system in non-Archimedean geometry. So have a meromorphic flat connection nabla. Now we just look at the connection. We suppose that U equals 0, and we ask that it's still second order pole there. So nabla U square du. It's second order pole in the U direction and the first order pole in all the other directions. In other words, if we consider nabla U square du and nabla U psi for any tangent vector field psi, then these are all regular. Okay, so that's definition of F bar. Any questions?
Why second order?
Why?
What is the significance of having second order?
Oh, I guess that from as I said, it's even better than second order pole. We have the exponential type. I guess that's observed from the examples that we want exponential type. So we have basic examples. To give you an idea what it may look like, you can say. So that's how the connection look like if you consider the pi direction. Say that the base B has coordinates pi, then it looks like we have some first order pole here. In the pi direction and in the u direction, we have second order pole, 1 over u squared. When we have this definition, F bundle, we have a natural action from the tangent space B to the bundle, restricted to u equals 0. So when we have a tangent vector, it acts by the connection in the direction u cosec. So we have tangent vector cosec, it acts by connection in the direction u cosec, restricted to u equals 0. It's like a residue. And the F bundle is called maximal at a point if we have some cyclic vector for the action. So it means that we have a cyclic vector H such that when we consider this natural action mu B, we get an isomorphism. B equals to mu H. We get an isomorphism between the tangent space and the fiber HB field. That's maximal. And in the maximal case, we have something called the Euler vector field, because here we are just looking at the, we just look at the residue, but in the direction side, but if we also take a look at the u direction, we have this operator KB. Nabla given by nabla u square is some kind of residue to nabla u square du restricted to u equals 0. And since this mu is the isomorphism in the maximal case, we get a u of B. It's the vector field that gives this action nabla u square du. And in the maximal case, we get a commutative product by the commutative product on the tangent space by the flatness of nabla. We can also consider logarithmic directions in the formal case. In the non-archimedean case too, but nobody really studied logarithm geometry in non-archimedean setting. In the formal case, we can consider the logarithmic directions. So we also can have some divisor there, and we consider logarithmic F bundle. And the same definition, except you replace tangent vector by log tangent vector. But you know this, even for A model F bundles, the log directions are necessary when we consider these curve classes, these Q directions, they are logarithmic directions. Okay, so since I was talking about this analytic decomposition theorem from Fourier transform, and that's for the non-commutative Hodge structure. Now we have this simplified or formal non-Archimedean version of F bundle, this F bundle, what kind of decomposition we can do for the F bundle. And that's what we call the spectral decomposition theorem. So recall we have this Euler vector field action KB given by nabla in the direction, residue in the direction u squared du. And we want to show that the generalized eigenspace decomposition of KB extends locally to a product decomposition of the F bonds. And that's directly motivated by this decomposition for the non-commutative quantum structures. And also, these eigenvalues are equal to these exponents or the singularities of this constructible sheaf or the exponents of the Stokes data that we have seen above. Okay, let me just state the theorem and state the theorem, and then I want to say something about its proof too. First, so for the spectral decomposition theorem, it's for F bundles, and for F bundles, we can do it either formally or in the non-Archimedean analytical way. In applications, we will use the non-Archimedean version, but to prove the decomposition theorem, first we have to prove it in the formal case, and then we do the estimates on the norms of the coefficient in order to show that it actually converges in the non-Archimedean sense. Here is the statement. In the formal case, we have a formal neighborhood. The base is now just formal neighborhood of some smooth point. And we have a maximal F bundle there. So assume we have some decomposition stable under this Euler vector field action. Here it's just a single operator KB. We have some decomposition, or you can just take the generalized eigenspace decomposition. And we ask that for this decomposition, the spectra of different pieces, they are disjoint. Then the claim is that this F bundle decomposes into a product of F bundles.
Sorry, if you're assuming that the spectra disjoint, why don't you just take the spectral decomposition?
We can just take the spectrum. But sometimes it's not algebraically close, or I don't know, Maxime seemed to want to say something else.
Yeah, but the proximal statement would be.
Like not algebraic. Okay, thank you for the remark. But for application, we actually need the non-Archimedean theorem. I stated the formal version first because formal version is needed to prove the non-Archimedean theorem. And it's just the same statement. Now the base is some non-Archimedean space. So some admissible open neighborhood of some smooth point. And we have a maximal F bundle there. We just need to assume it's maximal at one point and say that we have some decomposition, as Paul remarked. Why don't we say it's generalized eigenspace decomposition? And then the claim is that this decomposition induces a decomposition of the whole F bundle. The decomposition was just decomposition for one fiber at U equals 0. But it will induce a decomposition of the whole thing in F bundle into a product of maximal F bundles compatible with the decomposition we start with. So that's the one key statement we need for the application to birational geometry. So let me say something about the strategy of the proof. First, we need some version of the Frobenius theorem, which is just the Frobenius theorem in differential geometry. So you remember in differential geometry, when we have a commuting basis of vector field, we can integrate them and get the coordinate. And we need a formal version of that, and also a non-Archimedean version. So the formal Frobenius theorem, we have this formal affine space and some commuting basis of vector field. Then there exists some automorphism so that these vector fields come from coordinates. So there exists some automorphism such that under the automorphism, the vector fields are just given by the coordinates. Yeah, we can show that in order to find this automorphism, we can do it by solving some system of partial differential equations, and this system can be solved recursively. One can check that the indices just order by order, it works. So we can show that the Frobenius theorem works also in the non-Archimedean case. Here, we may need to shrink a little bit the neighborhood. So it says that when we have commuting basis of vector field, then by shrinking the neighborhood, we get the vector fields will come from some coordinates. And for it's the formal version plus study on the norms of the coefficients, we need to show that all the coefficients from the recursive formula, they don't grow too fast. They can be bounded so we can get a convergence domain. Okay. And in the second step, so now we have this Frobenius theorem. In the second step, we want to establish some decomposition theorem for the base. Because actually the spectral decomposition theorem, it's quite long to prove because it's just decomposes so many things. And we have to decompose them like one by one. So first we need to decompose the base. And the base has a structure of so-called F manifold, I guess introduced by Manning. And we need some decomposition theorem for this F manifold. Let me recall what is F manifold. That's the classical story. So an F manifold structure on the base is some commutative associative, so this OB linear commutative associative product on the tangent bundle satisfying so-called F identity for vector fields X, Y, Z, and W. And this is the F identity.
It's not a super manifold, yeah.
It's a super manifold, yes. Yeah, everything is super manifold, and that is the F identity. So it looks complicated, I guess. Manning, he deduced it from the product structure for Frobenius manifold, and he came up with this notion of F manifold. And we can also show that for F bundle, for maximal F bundle, we get this F manifold structure as well. And now we use this F manifold structure to decompose the base. Okay. So the theorem says that F manifold decomposition says that now we forget about F bundle, we just have F manifold. And if we have F manifold structure, formal or non-Archimedean, and if we get some splitting, for any splitting of the tangent space at B as algebras, if we get any splitting of the tangent space as algebras, then the whole F manifold is split into a product of F manifold. So that's how we split the base of the F bundle. And that's the second step. And after splitting the base or decomposition of the base, we need to split the bundle. And by the maximal, since F bundle here is assumed to be maximal, base and the fiber are identified. Sorry, the tangent space of the base and the fiber, they are identified. So that gives a splitting of the bundle. And but that only gives a splitting of the bundle at U equals 0. Because that's what follows from the definition of being maximal and we have to extend this splitting to the whole bundle. Again, by some other recursive procedure. Now we get a splitting of this bundle stable under this nabula in the direction u squared du by a recursive procedure. And in the non-archimedean case, we have to again look at the recursion and the normal coefficient to see that the splitting, because we have another recursive procedure here, and we have to show that it's convergent also in the non-archimedean case. And finally, we check that the connection decomposes according to the splitting of H, and each piece is fallback of some maximal F bundle on the BI, on the decomposition of the F manifold basis. Okay, so that's how a lot of steps lead to the spectral decomposition theorem. And then there is a natural question, because I motivated this spectral decomposition via the vanishing cycle decomposition in the analytic case by the Fourier Laplace transform. The natural question is, how is the spectral decomposition theorem related to the vanishing cycle decomposition from the Fourier Laplace transform? I remember, I guess it's also in the Miami conference when Maxime was talking about this blowup formulas. 2021. There is this vanishing cycle decomposition from the Fourier Laplace transform, and also some formal decomposition. So I was wondering how they are related to each other. And with my student Xiao, we showed that as a corollary of many other things we did, we showed that it corresponds to some specific choice of Gabriel path. This decomposition given by Fourier Laplace transforms depend on the choice of Gabriel path. So it was confusing because the spectral decomposition just seems something very canonical. And we showed that if we have this non-commutative Hodge structure of exponential type, then when we have this non-Stokes or non-anti-Stokes direction theta, if we have some direction, like general direction theta, and we look at choice of Gabriel path, or in this direction theta, starting from the singularities, and we consider the resulting vanishing cycle decomposition, and that's equal. That agrees with the formal spectral decomposition, but we consider its lift in the sector in this direction. Okay, and next let me talk about framing of F bundles. So the idea of framing comes from the notion of decoration on variation of non-commutative Hodge structures, also in the paper by Katzarkov, Kontsevich and Pantev. It also relates, it's used to relate non-commutative Hodge structures with like Frobenius older notions, Frobenius manifolds, and so on. Roughly, a framing of an F bundle is a local trivialization of this vector bundle H, in which the connection involves no positive powers of U. So we can give a precise definition. Local trivialization can be phrased as another flat connection on the vector bundle without poles, such that now if we take local trivialization given by that nabula frame, the framing connection, then the resulting, the original connection, now we can write it in this matrix form. And when we write it using the trivialization in the matrix form, we get no positive, no non-negative powers of U. So here we only get second order pole and the first order pole, and no other items, the terms, and there in the precise direction we only get U, 1 over U. That's what framing means. So framings do not exist in general. I think we don't know when framings actually exist or not exist. And if it exists at a point, at one point, then if there are no logarithmic directions, the framing always extends. But in the logarithmic case, it doesn't always extend. But we found a necessary and sufficient condition for it to extend. So the condition we found is, I don't know if we have agreed on the terminology yet. Let me just use terminology. So say that we have some formal logarithmic F bundle, and we say that a framing at this point B, we have a formal logarithmic F bundle over some base and point little b. And we say that a framing is drawn along the divisor D if for all tangent vectors psi for the divisor D, and we consider this endomorphism given by nabla U psi. And we say that this is independent of U. So we call it strong along D for this framing at B. And then we can show that in the logarithmic case, when we have framing already at one point, then this framing extends to a formal neighborhood if and only if it is strong along D. And in this case, the extension is also unique and explicitly determined. So we can show that the extension is always unique, but the existence needs this condition about independence in the D direction. That's the logarithmic case, and in the non-archimedean case, need some estimate on the convergence. So for the ideal proof, it's again solving carefully a system of PDEs. And I want to remark that this condition strong along D implies that for all tangent vector V in the direction D, if we consider this operator given by V, so given by nabla UV, and we consider its adjoint operator, it's 0. So add of this mu VV is 0. And we need this condition to make some recursive relations work, but this is not sufficient for the existence extension of framing. We need more. We need this independence.
So, sorry, Tony, what does adjoint mean?
Because it's endomorphism, adjoint. Consider the commutator with the matrix.
So you're saying it's central? No, what? It's commutator with what?
It's commute. Let me see. It's on this base.
Endomorphism.
Yes.
Scalar dimensions.
It's
No, he wants the action of mu B and beta B by
commuting with it.
Yes, commutation with this matrix.
So that means that matrix is central.
Matrix V X.
But acting well, acting on what?
On the endomorphism space.
So then it has to be a scalar multiple of identity.
Yeah.
Okay.
Yeah, I'm just writing it so we don't choose the basis. It's just a vector space.
Yeah. Proportional to identity. Only one is there. Okay, thank you. Wait.
So, thank you. Okay. So this extension of framing can be used to get reconstruction of isomorphism of logarithmic F bundles with framing. And when we have logarithmic, some isomorphism of logarithmic F bundle, assuming that one has framing, then we can reconstruct both the map, the bundle map, and also the map on the base uniquely and recursively from the extension of framing proof. So since all the framings, since we showed that like framing, if we have framing over one point, it can be extended to a neighborhood, then we also proved some theorem for the classification of framed F bundles over just a point. So we show that when we have F bundle over a point, and if it's framed, it can be written just by some matrices Kg, but of course, if there's still this variable U, still always matrices with entries that are power series in U. So, but wait, this Kg, they no longer have U. They are just the endomorphism of H. Yeah, and we have two framed F bundles of a point, H nabla and H nabla prime. So given by just the simple matrices K and G, and assume that K has simple eigenvalues, then these two F bundles, they are isomorphic if and only if there exists some endomorphism of H such that some phi, such that we can relate K and K prime by phi. And furthermore, in an eigenbasis of K, we have this Gii is equal to phi inverse G prime by II. So once these conditions are satisfied, these F bundles are actually isomorphic. And I want to remark that this theorem can also be extended beyond simple eigenvalues by considering matrices with the entries in the universal algebra. And finally, this theorem, classification theorem, and also the extension of framing theorem can be applied to decompositions of quantum cohomology, where we can strengthen the existence results and get the uniqueness result. Maybe let me just. So, for example, in the case of projective bundle, we have this natural splitting of cohomology of a projective bundle, and then we consider the maximal F bundle associated to the projective bundle and also the maximal F bundle associated to the joint unions of this basis space X. We have we can compare these two maximal F bundles.
What's delta and what's A?
Delta and A is to be determined in this theorem. So we can show that our goal is to get some isomorphism between them, and we can show that. So the idea is first to use our classification for F bundles over a point to get first isomorphism over that point, and then to extend this isomorphism from that point. And if we try to get isomorphism at points, we can see that we need some shifted base point given by this formula. And then we can use the extension of framing to get to identify the F bundles over some bigger analytical domain. So, okay, let me stop here and thank you for your attention.